So we move into modern cosmology. I use this term because in 2000 I was part of a summer school on the history of modern cosmology. And basically it was from 1905 up. So we're going to move into modern cosmology. Just to give you a taste of where our modern understanding of things like quantum physics, things like thermodynamics, things like relativity, where these came from. And basically they came from one source. There were other people working on it, but these 4 papers published in 1905 essentially became the foundation of our understanding of reality from that moment forward. So these 4 papers were published by Albert Einstein. And there's sort of, I don't know how it is in Germany, but in the US, there's kind of this mythology around Albert Einstein. Like he was really bad at math and he was a terrible student, which may have all been true. I would argue he was not very bad at math, but he was quite unhappy with the mathematics education system in Germany. And so he left. But he didn't drop out and he didn't sit and just think about things not connected with what was happening before. He was very cognizant of the developments in physics at that time. And he was very cognizant of the problems that existed at that time. So as we come in to what he's looking at, there were some problems. For example, there's what's called the Bentley's paradox, actually, Newton's paradox. And it means that if gravity works the way that Newton proposed, and that his laws and his mathematics were able to predict motion very well, very, very well. We could use his equations to do just about everything we needed. But there were a couple problems. One of them was that if gravity is pulling everything towards itself, how is the universe not collapsed? Because when we looked out at the sky, everything seemed to be really still and nothing was collapsing in on itself. Through his equations, there's an implication that time is infinite. So time has always been and time will always be. And so one of his responses was that the universe is infinite. So with an infinite universe, everything can pull on everything and it hangs in balance. But people noticed when they looked out into the universe with these nice new telescopes we had, that there was clumpy parts. So it wasn't all homogeneous. It wasn't all spread out. So how is it that everything stayed balanced? And when that conflict arose, this is a little bit the Aristotelian thinking again, that when the conflict arose with my perception of reality and what the mathematics and the science was telling us, you have to make a choice. Either you go with what you're seeing or you go with what you believe you should be seeing. And Newton went a little bit with what he believed he should be seeing. And the hand of God was what fixed that little problem, at least up until this point. And then there was a problem with Mercury. So the planets' orbits were a well-established problem. They could figure out where planets were going to be. Newton's equations explained why and how, but Mercury didn't behave quite the same as the other ones. And there was a little problem with the orbit of Mercury. It wouldn't quite stay in the same way as the other ones. And so they couldn't predict its orbit precisely. And then there was a little problem with light. So these Maxwell's equations that worked so well at creating the foundation of electricity, magnetism, utilization, so creating current, having people use electricity in their daily life, but it didn't work when things were moving. And there were some other small problems, but sort of really important problems in the existing structure. And so these are the problems that he addressed in these 4 papers. They didn't just come out of the blue. They came out of these existing questions that were going unanswered. So I'm going to go through just the 4 of them to bring this to close. So the first one, I'm going to leave the English here. I almost put the German, but then, so this is the English version. On a heuristic point of view about the creation and conversion of light. And this is actually what he won the Nobel Prize for. It had nothing to do with gravity or general relativity. It had to do with the photoelectric effect. So basically, what he said in this paper is light is also a particle, and so are electrons. A movement of electrons is what we call electricity. So this is the wave theory versus the quantum theory of light. So the time average is what we call wave theory. This is Maxwell's equation. And then there's this quantum theory. And this is, for example, how your digital camera works, things that you use every day. What they saw at this time was that certain metals, if you shone light on them, a current would come out. A current is just moving electrons. So light would create electrons. But the problem was, if you would just shine more light on the metal, more electrons wouldn't come out. And this was quite confusing. And what he found in this paper was that only certain colors of light affected the metals and created electrons. If you were to put, for example, this red light here, no electrons would be produced. This has to do with quantum physics, which we'll talk about in a couple of weeks. I'm not going to go into quantum physics too much today. But this is the foundation of what would become quantum mechanics. And he was not so clear on quantum mechanics for the rest of his life. He argued quite a bit with the people who were looking to fully develop the theory because it made no sense. And it still makes no sense, just to be clear. Quantum physics makes no sense. But he didn't believe it could be that way. It had to make sense. It seemed too random. But his work was the foundation of that randomness that he didn't understand to the day he died. His second paper was the investigations on the theory of Brownian motion. So Brownian motion was something that was actually discovered about 100 years earlier by a biologist looking through a microscope. And if you see a little fleck sitting, a little dot of something, a tea leaf, what's called a tea leaf, floating in water, the tea leaf will move. And it will move in this sort of crazy way we call a random walk. And so somebody who saw this one day decided we should try to figure out how this thing is moving and why. And they couldn't figure out, there was no sort of clear way to describe the movement of a flake of tea in hot water. And basically what this paper clarified is that atoms are a thing, and statistics, which is a field of mathematics that was sort of seen as not particularly useful to real-world applications, statistics too are quite important. And through this work, he was able to calculate the size of a molecule. And this paper became the foundation of what's called thermodynamics, the kinetic theory of heat. And it's using statistics to explain macroscopic events like this one. So basically, this tea leaf moves because these atoms or these molecules of water are bumping into it. And they're bumping into it in such quantities that they can actually move something much larger than themselves. So again, this is the second field of physics which essentially arose out of this insight. And so you notice these insights aren't huge. It's just a little shift in how we perceive things and what might be. And then we get to the weird stuff. So the third paper on the electrodynamics of a moving body. So basically what he said here is physics is relative. So there's this concept that the laws of physics are the same no matter where we are. And there was a little shift, which he said the laws of physics are the same no matter where you are, but how I perceive my little space and your little space is not necessarily the same, particularly when we're moving. And what he proposed with the speed of light is a fixed quantity. So for example, if you're, I'll tell this was an inspiration for my summer vacation. I come from Phoenix, Arizona. And in Phoenix, where my parents live, you'll see mailboxes that are fortified. They have like bricks around them. Because sometimes young people, when they're bored, will take a baseball bat while in a car and hit mailboxes and destroy them. And if somebody has gotten their mailbox destroyed a few times, apparently they fortify them in Phoenix, Arizona. So it's got me thinking about how to explain this. So if you hit a mailbox with a baseball bat, you might dent it. But if you're in a car and you hit a mailbox with a baseball bat, the mailbox flies, and it's kind of funny to some drunk teenagers in a car, I guess. So your speed of hitting the mailbox with your bat gets increased because you're in a car that's moving fast. That's how velocity, speed usually works. But if you have a flashlight and you shine it on a mailbox, the speed of light hitting that mailbox will be the speed of light. if you're in a car and you turn on a flashlight on a mailbox, the speed of light hitting that mailbox is the speed of light. So you add the speed of the car to the light and you still get the speed of light. So you add something to something and you get the same result, which doesn't make much sense. I'll explain it this way. So this is my friend Dieter Forster. He's a professor at Temple University, and he rides a bike. He's German, and he's the only person in Philadelphia who rides their bike to work every day. But I mentioned this series of talks, and he's a longtime mentor, so he had ideas, and I threatened to show a photo of him, and so he gave me this photo to show. So if Dieter is on his bike, moving through space at some speed, he's also moving through time at some speed. So the normal speed of time, does anybody have an idea of sort of the normal speed of time? It's about a second per second. So every second, time goes on for a second, only in one direction. So one of the implications of Einstein's work in this paper were that there's a speed limit. Essentially, there's a budget you get of total speed, including the time speed and the space speed. And that's indicated by this black line here. But if we put Dieter on a rocket and send him through space, his speed through space increases. We have the same budget of total speed that he's allowed to have, which means that his speed through time has to decrease. So his speed through time decreases from our perspective. So time in my world, where I am, is moving at a second per second. Dieter's world, it's also moving at a second per second. But when I watch him on the rocket, it seems to me that his time is not moving at exactly the same way my time is moving. And so this is a subtle but profound concept called space-time. So before this, time was this thing that moved at a second per second for everybody in all places. What this implied is that time is now a thing that can contract and stretch, like very much like space itself. So the term space-time means that now time is part of the material universe somehow. And this founded what eventually became what's called special relativity. Took another 10 years to become what's called general relativity. But for now, this is called special relativity. And this has all kinds of crazy, loopy results. So a lot of times we talk about time dilation. We were talking about a movie called Interstellar, which I can totally recommend. Interstellar had a fantastic science consultant named Kip Thorne. And he got the Nobel Prize last year and for the gravitational wave discovery, which is sort of the impetus for this talk. So this movie called Interstellar goes into time dilation really beautifully, because one of the implications of this work is that if you're close to a source of very strong gravity, your perceived time by an outsider will be different. So some of the characters in the story lose time compared to their ancestors back on Earth because they get close to a black hole. So the physics in that movie is very good. Just a heads up. Star Wars, not so much, but Interstellar is really, really good. So that's the third paper in this series. So the first paper was a foundation of quantum physics. The second paper, the foundation of thermodynamics and heat. The third paper, special relativity, which would blossom in 10 years once the math caught up into what's called general relativity. And the fourth one, I saw this and thought of the Zen Center. So E equals MC squared is not my coffee squared, but I think it's a good representation. And I'm pretty sure this is not a real photo. Just a little bit of fake news. So the inertia of a body, does it depend on its energy content? And what he found here is energy is related to the mass times light, the speed of light squared. So C is how we represent the speed of light as a constant. And what this was able to do was to unlock the power of the atom. So Lisa Meitner and Otto Hahn, quite a while later, so about 30 years later, finally were able to use the information from this equation to predict how we could split the atom. So Lise Meitner did the theoretical work with her partners, and Otto Hahn did the experimental work in the lab. And it's a very interesting story. Lise Meitner was in Berlin. She was actually the first female professor of physics in Germany. Unfortunately, she was also Jewish in the late 1930s. And so her collaborators, including Otto Hahn and some from Northern Europe, smuggled her out of the country. In fact, Otto Hahn gave her an engagement ring, a family heirloom, to take to bribe the guards in case they couldn't get her across the border. And so she luckily made it out safely and reestablished her research program eventually in Stockholm is where she landed. And they continued to collaborate via letters. And so he would do the work in the laboratory, send her the results, and she would give the theoretical understanding. So she was the one who figured out sort of the last piece to unlocking nuclear fission. And in 1944, Otto Hahn won the Nobel Prize for it. And so this question of time comes back again. So what is this thing called time? Is it a measurement? Is it an experience? We'll talk a little bit about the experience of time versus time itself in the third talk. But this concept of time is sort of what's bringing people forward in their search to understand cosmology in the universe. It began simply by understanding sort of day and night, seasons moving, when we plant things, when we harvest things, when we perform certain rituals. And we required it to be a bit more precise as we tried to really answer some of the unanswered questions. And in all of this time was a background player. So time was sort of assumed to be a fixed thing. And at the beginning of the 20th century, time was no longer fixed. Time was as free as anything else. We can use this as a source of contemplation. And just like this growth that we saw in the Fibonacci sequence, everything grows sort of exponentially. Our knowledge exploded at this early 20th century mark. And we'll talk about the implications of that in the next week and the week after. And then in the fourth week, we're going to talk about the Nobel Prize from last year, so the gravitational waves. This has a particularly special place in my heart because 20 years ago, I got to work for a short period of time in the collaboration. And Kip Thorne was my mentor. He was the one directing the program at the time. And in that space, I had went from a student sort of doing my studies every day in the classroom. You know, you do your studies, you do your grades, and you feel like, what's the point? And when I had the chance to work in this collaboration, I realized that I was part of a lineage of knowledge. Even just my little part of sort of, figuring out my problem and presenting it. And so that each one of us has a part to play, even in this knowledge, even if it's sitting and contemplating in a dark space, the sky above. This is a famous poem by Sarah Williams. I encourage you to look up the entire poem because it's a beautiful way to express the beauty of lineage, of handing down knowledge from generation to generation. It's called The Old Astronomer. And one of the beautiful lines you see often used is, "I have loved the stars too fondly to be fearful of the night." And it's the story of a dying astronomer talking to her pupil just at the end and sharing what they've shared together and trusting that the student will take it and continue on from there. And so I'm going to leave this here.